I'd like to thank the organizer to allow an opportunity to present here at a very historic site. This work is a joint work with Henry Chuan of NCEP and a discussion with Yoshimura-san of Metallurgical Research Institute, JMA, and Niels, ACMWF, were very helpful. So now I'd like to discuss vertical coordinate based on hydrostatic pressure. And it is natural to use Z-based, height-based coordinate in non-hydrostatic model because pressure is no longer single-valued monotonic. But there is alternative to height-based coordinate. That is hydrostatic pressure-based coordinate. That is hydrostatic, so monotone in the vertical. And there is no additional metric terms like Z star coordinate. And it is easy to conserve energy. And if you move from hydrostatic to non-hydrostatic, you need to add two more variables, for example, W and P. Laprise and Chuan independently propose this idea. Like Sgt. Pepper's Lonely Hearts Club Band, they celebrate a 20-year anniversary. So at this opportunity, it is good to revisit the idea. To begin, I need a little help from seminal work by Kazahara, additional 22 years before. If height Z is function of horizontal coordinate C and also single-valued monotonic general coordinate S, the gradient of any scalar A are expressed in two terms now. In this talk, I'd like to use sigma coordinate for simplicity. We don't have Tibet in Japan, so we don't care much about high terrain. So we have two terms here. And in pressure gradient terms, Laprise reached this equation and Chuan reached this equation. They started from Euler equation in Z coordinate and transformed into eta or sigma coordinate, but they reached the different second term. Why they reached these two second terms? That is one of my motivation. I'd like to understand the difference. The difference comes from the definition of geopotential height. Laprise integrated a full density, whereas Chuan used a hydrostatic variable to obtain geopotential height. That was a difference. So now we have choices for hydrostatic temperature in Chuan's formulation. Hydrostatic temperature can be time independent. That is probably only useful in idealized situation. And in MSM, default is this externally given hydrostatic temperature. This is only useful in limited area model, where you can get externally hydrostatic temperature from the global model or coarse model. And so Chuan introduced internally evolving hydrostatic temperature as equation 11. But you have to add this equation, and you have to calculate this. So I thought it would be nice to have an option to diagnose hydrostatic pressure from other variable. So let's go back to Laplace formulation. He defined geopotential height using full density. So it implicitly assumes hydrostatic density is equal to full density. Using equation for ideal gas, you get the diagnostic relation for hydrostatic temperature. Another hydrostatic state comes from Araka's and Corner paper. Using hydrostatic equation expressed in external function, this implies that the hydrostatic potential temperature is equal to full potential temperature. And you get equation 17. The only difference is its power, kappa or 1. So there is a convenient identity. So if you define Q prime as logarithm of full pressure minus logarithm of hydrostatic pressure, so you get T over T bar. Bar means hydrostatic variable, exponential of kappa Q prime. Using this identity in a pressure gradient term to eliminate hydrostatic temperature, you get equation 20. And you can replace kappa with 1 for the hydrostatic state of Laplace at any time. In addition, we need to obtain a gradient of hydrostatic temperature. This can also be expressed with full temperature and Q prime. And this is also used to obtain vertical velocity and divergence, three-dimensional divergence. Now, I'd like to show the test using NCEP MSM. MSM is a non-hydrostatic version of NCEP RSM, regional spectral model, described in Chuan and Kanamitsu, 1994. It uses Euler equation transformed from Z to sigma coordinate as we have seen. NCEP MSM uses horizontal discretization of double Fourier series. It shares the same physics package when the MSM were developed with NCEP GSM. And often it uses the same vertical level. And it uses the perturbation method. And what is perturbation method? The perturbation method, it only updates the deviation from the basic field as described in equation 24. In a limited area model, it calculates fine scale, but also you can calculate large scale, small wave number motions. Those motions may not be accurate because the domain is limited. So in the perturbation method, low wave number motions are replaced with global, those of the global model, and only updates the fine scale. So first, we'd like to look at the idealized case, pseudo two-dimensional experiment. Physical packages are turned off, and I use the Mercator projection near the equator using the horizontal resolution of 10 meters. And we have a FFT-friendly 128 grid point in x direction. And there are 8 identical cross-section, xz cross-section, to represent two-dimensional flow. And you get very small meridional flow, like 1 to 10 minus 10. But you can safely neglect this small meridional wind. The thickness of sigma is 0.01 below 0.84 sigma, and gradually stretched from 0.002 to 0.64 above sigma 0.84, and there are 180 levels. And I use a time step of 1 second, and no diffusion or boundary relaxations are used. So the warm bubble experiment defined by Robert, 1993, and we have temperature profile on the left, and below 0.84 sigma, we have isentropic atmosphere, and above that we have isothermal atmosphere. And at the center of the domain, we have a temperature anomaly, and within the 50 meter, that is constant value of 0.5 Kelvin. And away from that, there is a Gaussian distribution with a E-folding radius of 100 meter. This is the result at the 6 minute. On the left, this is the default of MSM. This is my first non-hydrostatic experiment. I've been working on hydrostatic GCM, so I'd like to share. I'd like to ask you to share my excitement. And on the right, this is modified MSM with hydrostatic state of Araka and Kona. And these two look very similar. And if you have very good eyes, this warm bubble is slightly higher than the default, maybe not distinguishable. I replaced the default one with a hydrostatic state of Laplace. Also, this is very similar, and especially these two are similar. This is zonal wind, convergence below the warm bubble, and divergence at the top. And this feature is reproduced with the modified case. So this is a case for the Araka and Kona hydrostatic state. And Laplace hydrostatic was so similar, so I only show Araka and Kona result from now on. And this is the vertical velocity. And again, this is the magnitude and locations of the vertical velocity is very close. And finally, I'd like to show focus experiment. Initialized at a certain day in summer last year, and I conducted a 24-hour focus. In this experiment, we have a full physics package, and I used a horizontal resolution of 26 kilometers. I know that this is not in the non-hydrostatic regime, but this is a test to see if my modification works. I used 42 level, and the time step is 60 seconds. And the initial and the boundary conditions were taken from NCEP GFS. And this time, I used a polar stereo projection. The domain is near Japan, centered at Kyoto. And the problem size is 32, 32, and 42 levels. Only one slide for this experiment. This is sea level pressure, initial condition, and the other panels are 24-hour forecast. And this is a default of MSM, and these two are hydrostatic diagnostic hydrostatic states. So 3 are similar in my opinion. To summarize, although both Laprise and Chuan transform the Euler equation in z coordinate to eta hybrid or sigma coordinates, different definition of geopotential height result in different forms. Laprise implicitly assumed that hydrostatic density is equal to full density. Similarly, Arakan-Kona assumes that hydrostatic potential temperature is full potential temperature. These assumptions led to the diagnostic relation for hydrostatic T. So you can use alternatively to prognostic hydrostatic temperature. And I conducted warm bubble and focus experiment. And these two hydrostatic states, the model worked very well. And I need to conduct more tests, like one with orography, but I should use higher resolution in the realistic case. But I think the hydrostatic temperature does not, the prognostic relation of hydrostatic temperature does not appear in the energy conservation, although there is a geopotential in energy. So any kind of reasonable hydrostatic temperature work. Okay, that's all for me. Thank you very much.
Well, that statement for Connor and Arakawa is not accurate.
No.
That what you wrote over there, theta bar is equal theta, is not accurate.
Not accurate?
Theta is non-hydrostatic. Z is non-hydrostatic too.
Z can be
Yeah.
Oh, is that
so
right?
using hydrostatic equation does not mean everything in it is hydrostatic. So if theta non-hydrostatic and Z is non-hydrostatic,
But
that statement is not accurate.
In fact, you could make the same statement with regard to the Laplace line with rho bar equaling rho. Again, the hydrostatic pressure equation assumes that the PDZ is G rho, but that rho can be as whatever it is. There's no assumption.
But hydrostatic equation is part of vertical momentum equation, and
Yes, but
hydrostatic balance is only achieved with hydrostatic state.
That is not accurate. Hydrostatic equation can be used. Z could be non-hydrostatic, and theta is non-hydrostatic, but the what you are pressure could be hydrostatic.
You know, in that geopotential equation, you have dphi dp hydrostatic, right? But that phi, the height, it doesn't have to be hydrostatic, and the density doesn't have to be hydrostatic. Because it is a fully, I mean, Laplace's equations are without approximation, right? They are the full non-hydrostatic equations.
But if you admit that the, in my opinion, here P ignores other terms other than hydrostatic balance in the vertical momentum equation. Silent.
Well, I would say not.
Let's discuss
Anyway,
later. Other questions. I think other questions.
Any other questions? Comments? Well,
Okay, thank you very much.